So welcome to, and thanks for coming, and welcome to the last Artsci Salon of the fall. We had 4 very beautiful, incredible, and inspiring events. 2 of them are archived at Fields, so you should check them out. And today we are doing double streaming. So one will be like the regular one, but then we have some more interactive streaming. And eventually, if somebody from home wants to ask us questions, they will be able to. So today's Artsci Salon is titled Icicle Music. Thanks to Stephen's inspiration. And we have 3 guests. Stephen Morris, who will talk right now, Jimmie LeBlanc, and Fareena Chanda. I'm just introducing very briefly Stephen, but you guys all know him already because he's one of the organizers of the Artsci Salon. Stephen Morris is the Tuzo Winston Professor of Geophysics at the University of Toronto, and has been collaborating with artists for a long time. And last year we had another talk with him and 2 other guests, also about another collaboration that they did, or like intellectual. So today, but today I think that this collaboration is more deep. This collaboration was a part of the Continuum Ensemble, and it was presented for the first time at Subtle Technologies Festival in 2015, I think in May. It was a great success. So we will show, I think, some excerpts from it tonight, and we hope you enjoy it. So.
Okay, thank you. Now, we usually turn the lights off, even though it's kind of...
I'll turn it off.
All right.
Which one?
Just, yeah, well, no, leave something on.
Okay.
All right. So I guess my job is to tell you about the background science that we started with. This is kind of a long-term project that I've been working on with several students over several years, and it's kind of I admit, a kind of crazy thing. We're interested in the morphology of icicles, and you may be surprised to hear that we cannot explain the shape of an icicle. You can put in all the physics that you know, and you can try to calculate the shape of this mundane, everyday object, and you discover that the equations just blow up in your face and you can't do it. And so even though you see them every day, they're a class of systems which we don't actually have a simple explanation for their shape. And the reason for that is quite simple. They're emergent. You put in some conditions, some water flow and some temperature, and nature decides to make the icicle by a kind of chicken and egg process. As the icicle forms, the shape determines how the water flows over the surface, and the water flow over the surface determines how the shape forms. And so the thing is a kind of self-organized feedback process. And those are the very kinds of things that are very difficult to sort of write down equations for. So there's actually quite a bit of theory, and I won't show you any theory at all in this talk. There's quite a bit of theory and quite a bit of anxiety by applied mathematicians over trying to explain things like this. And our interest was to try and take this very obvious natural phenomena into the laboratory and just control the hell out of it, and learn as much as we can about the formation process and everything. And this has been a project. I hate to tell you this, but I've been working on this for more than 10 years. Okay, the first icicle machine was built at Cambridge in 05-06, and it was kind of the Mark 0. And now over in my lab in McLennan, which is a couple of doors up the street, we have the 10th version of this machine. And the quest goes on because we're still not there. So here's the machine. Just to go straight to the technical details, it's basically a box about the size of a beer fridge, which is covered with foam, and it's refrigerated by these white commercial things which circulate good old Canadian Tire antifreeze around the box. And there's me for scale. And at the other end, there's a camera. I think the next picture is Anthony Chen. Yeah. So this is Anthony Chen. He's the graduate student who now works in Calgary. He wrote his PhD and built the machine and generated almost all the data, which I'm going to show you. And here's a camera which is looking into there's actually a hole there when it's working, looks into the side of the box. And inside the box we have a little support, and we pump water in very slowly, and it drips off the support. The box is refrigerated, and there's lights in there so we can see it. And we measure the temperature and the humidity and the flow rate and the cleanliness of the water and everything you can think of, and we grow icicle after icicle in the box. That's the basic thing. And the camera records the shape of the icicle in a way which I will describe. Okay, so here's the actual, see this weird ghost thing. We got to get rid of this. That's a Fields Institute thing. It is. It is. I can't understand it. It's got nothing to do with my computer. All right, so here's an icicle. Oh, it's okay, so I'll click twice. So here's an icicle growing. And the other thing we do, which may surprise you, is we actually rotate the point of support. So there's a little kind of pointy dowel at the top of the experiment, and as the water drips in and the icicle forms, it forms on a rotating support. Now, keep in mind that icicles grow very slowly, so each second of this movie is about 15 minutes of real time. So it's a very, very boring experiment in real time. The icicle takes 4 minutes to rotate. You can barely see it move. And it takes about 8 hours or something like that to grow down to the height. This distance here, by the way, is 65 centimeters, so it's kind of about that tall. Why rotate the icicle? Well, there's a whole bunch of reasons, but the first reason is that it's just cool to do, you know. Nobody's ever seen a rotating icicle before, so we made them anyway. But the other reason is that the computer can take a picture of the icicle 8 times per rotation, and we can train the computer to measure the outline of the icicle in the picture. So we can, without using our eye, we can analyze the shape of the icicle, and I can even take the 8 projections of the icicle and put them back into 3 dimensions again and extract the full 3-dimensional shape of the icicle as a function of the time. So 4-dimensional data, okay? We know the shape, all 3 dimensions of the shape as a function of time. And also, we'd like the water to flow uniformly around the icicle, so we drip in with a nozzle which is slightly off axis like this. So it's like turning your meat in your barbecue to make sure all sides of it are the same, okay? So this is actually a distilled water icicle, and it's actually, this thing doesn't work very well. It's jerkily turning. It should be turning smoothly. And we collect the water that drips out, and we can actually weigh the water that goes in, weigh the water that goes out, control everything about how much ice is formed and so on, okay? So that's basically the icicle machine. Here's another view of the icicle machine. In order to know the orientation of the icicle, we have a set of tabs around the top. So the icicle is growing from this support downward into the board. And as these tabs pass through a little gadget, which I'll show you in a second, it triggers the camera. So we actually have discrete angles that we know the shape of the icicle at. And this actually comes up again when we talk about the music, because we can either present the data as a sequence of tabs, in other words, as a sequence of rotational views, or we can isolate a single rotational view over and over again. So we can look at the thing as if we watched it from one direction and watched it grow, okay? So here's the little interrupter gadget, which when the tab passes through it, it triggers a little circuit, and that fires off the camera. Okay, and using this device, we can grow all kinds of different icicles. And there's some odd things that we discovered right away. One is that if you try to do the experiment without stirring the air, so there's no air motion in the box, then the icicles have a tendency to grow these things we call legs. So as the icicle grows, this is time lapse, so this is different times. This one decides to grow a little prong here, and that prong just continues to drip, and it grows an extra leg, okay? So those are multi-tipped icicles are quite common. And this happens when the air is not stirred. Now you're going to ask me, well, why does it matter whether the air is stirred or not? Well, the answer is we don't know. If you stir the air rigorously in the box, the icicle grows a little faster, and it has a tendency not to grow the multiple tips. It's not completely guaranteed that it won't grow multiple tips when there's air stirred, but it almost always does when you don't stir the air. Now, if you would like to go and make a theory of why this is true, then I'd like to hear it, because we don't know why. Okay, well, there's some ideas, but we don't really know why. The thing we've really spent a lot of time studying is the ripple pattern that develops on the icicle. So these are 3 different icicles. These are all natural ones, actually. These 2, this one and this one grew on my house, and this one I actually pulled off of somebody's webpage. And what you see is that icicles don't always form, as I just showed you, a nice smooth icicle growing out of distilled water. You also see icicles which have this undulatory shape, okay? But not all the icicles you see are like that. They have a tendency to be like that. And the reason is quite surprising, is it turns out that if you grow an icicle out of distilled water, it forms a nice smooth shape. And this is a distilled water one. If you put in a tiny quantity of dissolved impurities, just as much as impurities as you have in Toronto tap water, which is not very much, you start to see a clear ripple pattern on the outside. And if you keep adding more impurities, the ripple pattern just gets bigger, okay? And so this is what we call scientific tap water. It's basically distilled water with a tiny quantity of sodium chloride added to it to make it just as impure as tap water. And unfortunately, the theorists from Japan who wanted to explain these ripples spent about 8 years writing complicated mathematical theories of the ripples without taking into account the fact that the impurities had to be there, and we discovered that the impurities had to be there. So you're going to ask me why the impurities have to be there to produce the ripples, and the answer is we don't know. There's no theory. But the ripples will be important to our story because they give you this beautiful structure. And I'm actually more interested in the ripples than I am in the overall shape of the icicle. Okay, so here's another strange feature. Here's two icicles. This one has a rather low level of impurities, and now I'm animating only the views from one direction, so you can just see it growing as if you're seeing it from one direction. And here, if you look very closely and study the ripples, you'll see that they move slightly upward during the growth. Can you see them? Just put your eye on a bump there, and you'll see that it's moving upward slowly. Meanwhile, if I put more salt in, you can get multiple tips. There's a multiple tip. But if you look at these ripples, they're quite a lot bigger. But I think you'll agree that they're actually moving downward. Oops. Okay, this is driving me nuts. Okay, so if you put your eye on a ripple here, you'll see that it's actually traveling downward. Okay. No ice is moving. What's happening is, as the water flows over the icicle, it's forming on the upper surface of the existing ripple a little bit more, and that causes the ripple to grow slightly higher than it did before, and so that causes the ripple to move upward. And conversely, in this condition, they move slightly downward. And just to show you one piece of data, this is the velocity of the ripple as a function of the salinity or the saltiness of the water. And, small salt icicles move up, and low salt and high salt icicles move down. And there's a kind of sweet spot of about 0.1 weight percent where the icicle ripples don't move. Now you're going to ask me, why do the icicle ripples move? The answer is we don't know. There's no theory, okay? It's a complex phenomenology for which we have no explanation. Okay, so after we finished the main scientific project, I felt kind of stupid because we had taken about 230,000 images of icicles. About 250 icicles were grown, and the thousands of images of each one were taken. And we can assemble those into movies. We could do all kinds of things with them. We analyzed all kinds of data. But we still had this huge trove of pictures. And in this age, it just didn't seem right to keep them to yourself, right? So we created this thing called the Icicle Atlas, which is an open access data set of icicles data. All of you can now Google Icicle Atlas on your phone and pull up more pictures of icicles and more data about icicles than have ever been gathered before in the history of humanity. And it's all open source. I convinced the library to give it an open Creative Commons 4.0 license. So that means you can do anything you want with it. You can make Christmas cards. You can do whatever you want with it. And this is what the front page of each run of the Icicle Atlas looks like. There's a picture of the icicle in question. There's all the movies that are all assembled there. All the raw images are available. They're all zip files. All the maps of all the ripples are there. Everything's there. So there are more than 400 movies, and there's 237 separate icicles and about 1,000 images of each icicle. And what can you do with this? Well, what I did, I got rid of it by going backwards and forwards. What I do is I made a kind of searchable rogues gallery. So these are thumbnails of a small fraction of the icicles, and you can just go here and click on. You think, oh, that's a pretty one. And you can click on that, and you can have all the images you want of that icicle, all the movies and everything. Okay, so it's like a rogues gallery. Each icicle has its own little Facebook page, in effect, right? And the other thing you can do, as I mentioned before, is you can take that three-dimensional data and you can project it back into a three-dimensional STL file for those of you who are interested in these things. And this is the actual icicle, and this is the STL file, and I'm turning it around in the computer. And then you can take that thing and you can send it to a 3D printer. So here I have a couple of icicles. They're actually the same icicle printed at the Semaphore Lab in Robarts. And you can pass those around. And so it's kind of uncanny. These are icicles that melted, 3 or 4 years ago. And now we know their whole three-dimensional shape, and we've reconstructed it in a 3D printer. And so right now, just a few months ago, I uploaded several tens of thousands of 3D printable files to the Icicle Atlas. And right now I'm working on getting them into the Thingiverse and to Shapeways and all these online places where people find 3D files. And I'm just going to be amused by whatever it is that people do with them. I've also been interested in kind of mashing up the data. So I wrote some Python code that randomly selects icicles from the atlas and composites them in various ways. And I'm having actually an art show, not entirely about icicles, but partly about icicles, at the Redhead Gallery in this second 2 weeks of January with my friend Ron Wild, who unfortunately is not here tonight. But Ron is the artist who makes the collages, which are up in the Fields Institute outside here. And Ron and I are going to have a show, and I'm going to put some of these icicle art collages, if you like. But these are collages that are partly selected by the computer, okay? So here's one, 11 random icicles from the Icicle Atlas. Just to give you an idea of the diversity of the morphology of the different icicles. And the funny thing is, I've been staring at these for so long, I can tell you that this one is saltier than that one, distilled. And I know that this one stopped growing because it's a little fatter at the top, and this one's a little fatter. So these are my friends. I know these icicles. So here's another one. I call this a 17 titch. It's a 17 random icicles from the Icicle Atlas, just to show you the advice. Here's the one with the extra leg. And then I also wrote some code to allow me to not just composite them, but also composite movies of them. And if you're interested, I'll give you this code, and you can make sort of random movies. This one, the indexer was a little wonky on that one, so it jiggled around a little bit. But these are all taken from a single point of view. And there's all the run numbers. And this is all generated by a Python code which fetches the images from the atlas, okay? So it's kind of automated compositing, just for the heck of it. Okay, so that brings us to the musical event itself. The idea was to take this fascinating data and extract it and do a little processing on it, and then hand it over to Jimmie and Fareena, who handled the art part of the project. So this icicle, run 110823, is the icicle that was used for the composition that they're going to talk about. And these are the two different ways of looking at the data. This one is the icicle in rotating, so every picture animated in a rotating fashion. And this is the icicle repeatedly growing from each different rotational point of view, okay? And we can extract both the left and right edges of the icicle, and the edge which was actually used in the composition is the left edge of run 110823. So we know very precisely which one it is and what the conditions were and everything about it. And so here's the front page of Continuum Contemporary Music's homepage, and the event took place on May 28th, and the event was called Collide, and this was, I think, the first piece of the event. And Fareena provided a video installation that went with it. But there were several other works that were presented on the same evening. And the sort of front-end picture of the Collide event was this sort of animated, mixed-up thing of Icicle. So here's what the data that was eventually... that's shit. Okay. Now I've screwed it up. I want to know why this thing does this, and I don't want to do it anymore. Okay. So this is the massaged ripples of... actually a kind of late stage of the icicle's growth. So this is the top of the icicle. So if you imagine it turned this way, this is the ripples at the top of the left edge of icicle 110823, and these are the smaller ripples toward the tip. And we also extracted shapes from earlier in the icicle's evolution. So you could, for example, take one when it's younger and older, and basically this time series just gets longer and longer. And you can hear all this in the music if you listen carefully. So Jimmie and I had a very fun time going back and forth. I would send him a waveform. He would send me some composed piece, and we'd go back and forth. And you could hear the icicle getting longer, and you could hear the ripples repeating themselves and so on. But this is sort of the data that was generated from the Icicle Atlas data, which was given to Jimmie, and he did what he is about to describe with it. Okay, so I'll hand it over to you now. While he's getting his computer set up, I'll answer any questions. Oh, okay.
I
I'll take, if anybody has any questions about the scientific aspect, why don't you get your machine going there?
Give him a round of applause.
Yeah.
You do understand about this going on.
We have a detailed theoretical model, which I'm sure is not completely wrong. And we know precisely what it is that we don't know to make that model work. It involves two moving boundaries, differential equations for the temperature and the salinity of the water, and 9 boundary conditions, and fluid mechanics. And that's just the linear theory, okay? Navier-Stokes, yeah. So basically what we're trying to do theoretically is we're trying to take an infinitely flat, infinitely wide icicle with a thin film of perfect water running down it and perturb that surface infinitesimally with a ripple and then ask whether that ripple will grow or decay mathematically. And if the theory worked, it would tell us that a ripple, I forgot to mention that the ripples are always 1 centimeter in wavelength. It should account for the fact that the ripples grow at that wavelength and that they move in the direction that they move. What happens is it turns out the theory predicts infinitely small ripples grow infinitely fast. So in our language, it has an ultraviolet catastrophe. And this can be traced to the boundary conditions on one of the equations, on one of the 9 boundary conditions. So yeah, we have a very sophisticated theory of what we don't understand. And there's some hope that we'll get the theory to work. But ice, it turns out, is a very complex material. It's not just as simple as you might think. Yeah.
Is there significance of the 65 centimeters?
No, that's just the size of the box. The magic thing is that the ripples are always 1 centimeter wide. And I didn't show you the data, but we varied all kinds of different things. And the new experiments will actually try different impurities. We just used a simple impurity of sodium chloride. There are these fish that produce these proteins which inhibit ice growth, which allows the fish to live in Arctic sub-zero water. And they're called antifreeze proteins, and they do interesting stuff to the surface of ice. So that's one possibility. We could put in dyes to look at where the dye goes inside the ice. And so there's another whole PhD project, believe it or not, in there. All right, are you ready? So you got to wear this for recording purposes.
Okay, so there's another one there actually. Well, anyway, so I'm going to introduce the two artists now. Jimmie LeBlanc is a composer and guitarist, and you're from Montreal. You're based in Montreal. You have a doctorate from McGill, from the Schulich School of Music, and it is interesting because your music is very much informed by philosophy. There's quite a nice, very, very interesting intersection between making music and philosophical thinking. So that's another intersection that we have to think about. Next will be Fareena Chanda, who is an interdisciplinary artist. She's a designer and a researcher also, who uses process-based inquiry to explore themes of self-knowledge through time-based media and installation art practices. And she took care of the installation part of this project called ICE. So, thanks.
So, it's working. Yes, you hear me? You hear me well? So thank you for being there. So we'll start my part of this presentation. So I will talk about the compositional aspect of the music that I've produced for this event that was thought of as an installation. So it was thought of as a video installation with music. And how it happened at the Solar Technologies Festival last May is that it was, I don't remember the name of that theater, but you had a space downstairs which was called the theater center. And so in the incubator you would have the installation by Fareena, which was 3 screens like that. People would go in that enclosure. And at the same time, in the main venue, the musicians from Continuum Ensembles, and you see the instruments that were used there, would be on that main venue with one screen reproducing one of the screens of the installation downstairs. So the show was running in two spaces at the same time. And so the idea was the music and the visuals would be thought of as an immersive experience for the listener and the spectator. So for the composition of the music, as Stephen has already said, it was based on the data from his research on the Icicle, the formation of Icicle. And I will show how exactly it was done. So if I try to just put it in a more schematic way, there were maybe three main components to the composition. So first, the instruments themselves, so the ensemble, flute, clarinet, violin, cello, piano, percussion, and an electronics part, which was a fixed tape, so sounds, recordings of ice and snow that I will also illustrate, that was going with the music for the instrument, and they were meant to blend together to create an overall texture, and the video installation. That was what was on top of that. So this was the instruments, this was the tape part, and maybe another aspect of the composition that is important is how we would organize the different moments, so the form of the event over time, how we would evolve. So our basic premise was to imagine that we would move from a more flowing, moving type of situation towards more free frozenness or frozennicity. So as if something was going towards getting frozen at the end. So this would inform the way we would approach the texture for the music and also the visuals. So now, to be more precise, these are representations I did from the curves that Stephen sent me about the observation of those ripple formation on the icicle that you have seen. So 111023, that one, that guy. So he already explained what were the tabs. So you see here different times of tab 1, all right? So for that icicle, Stephen sent me 8 different tabs, having 8 each between 38 and 39 times of information.
Actually, I think the rotations. That's the rotation number. The rotation, the time multiplied by 4 minutes would be the time of the
Yeah, I think what I understood is that there were 39 different takes from one. Yeah, because I didn't have all the readings that you've taken because it would have been too much data. So it was kind of a sampling of spaced moments of that evolution.
You see the answers getting longer.
Exactly.
And the ripples getting more and more complex.
One was looking at one icicle from one direction and at those times. I used all the 39 times, but I'm just showing you here a sampling to see how the curve is getting more and more complex. And I would have 8 tabs, so 8 directions. And what I would do for the composition of the piece is to go through tab 1 through 8 with time 1, and then again tab 1 to 8 with time 2, and 1 to 8 with time 3. So it's as if the icicle is literally rotating. And so I would use all those waveforms. Well, I'm calling them waveforms because the idea was to use those curves and to imagine that they would be the cycle of a waveform. So repeated at a certain frequency. So as you know, the most simple waveform we have is the sine tone, the sine wave. So it's this shape there. And if you repeat that at a given frequency, and I used for the purpose of this experiment 55 hertz, so it's a low A. And so if you repeat that shape at that frequency, it gives an A with a given timbre. But if you use a different shape for the cycle, It gives a different timbre, but still the same frequency. Okay, you know the principle. So as the icicle is growing, the waveform is getting more complex, and so the timbre is getting also more and more complex and more dissonant. But even the first stages are already complex for a waveform, so it's already like complex, but still it's more harmonic. And as we get to the last times, then we get a more inharmonic sound. And so I used the technique called wave shaping to produce that using a software that is called MaxMSP, so I could hear exactly how they sound. But when I was hearing how they sound, I wanted to exactly know how they were, what were the partials and the harmonics that were contained into those sounds. So I did sonograms of each of those sound waves. And here you see the sonogram of tab 1 times 1 to 39. So you can see the 39 slices of time. And so you can imagine that each curve is more and more complex. And so you can see also the energy in the sound that goes gradually up in the spectrum. And so as it goes up, so what is more yellow is what we are the strongest partials. What is blue is the lowest partials. So as we evolve over time, we get more and more higher partials that are more dissonant by nature. So we hear that we go from consonance to dissonance. And I will play you how it sounds like really the raw result of the wave shaping that I've done. So you will hear the 39 stages. I'll play it twice so that you have the time to... Okay, just once more. So it gives the impression of an opening up of the sound. So the metaphor of the icicle growing is really clear. And so after that stage, I needed to know from the sonogram what were the actual pitches. So I used another software to translate them into actual pitches to do the music. And the idea was to use this pitch material for the instruments, the actual instruments. But you can see it's very complex. So what you have on the upper system is the first times of tab 1. You see that we have more sound in the lower part. They are more spaced, but still there's complexity also in upper regions. But it sounds more consonant. But as you arrive at the latest stages of the growing process, it's already clustered in the top registers, and it's really dense and really dissonant. So here what you see are the strongest partials of the sounds. So because of this complexity, I was not really interested in that as a raw result this was not informing the musical idea I had in mind exactly, but I thought I devised a way to filter out the data that was there to get something that was more rationalized somehow. So I've created a chord progression that was really simple based on triadic chords. So C major, A minor, a progression that I just composed. And I imagined to filter out this content, which is really rich, that, for example, when I'm on a C major segment, I would just keep all the pitches that are close to the notes of the triad. So close to G, close to E, and close to C. So close to means that for C, I would keep also B and B, the microtones that you can find in between, let's say, a certain cluster around C, certain cluster around E, and a certain cluster around G. So using that process and reorganizing the chords over the register, I would get this type of sonorities there that are much more, that are clearer, for sure. And from one stage to the other, you can hear more what's happening in terms of color. So I play it to you like the raw result, because what I did from there, you see all the stages of the process to arrive to the score. Huh? It's not yet for the instrument. From there, I wanted to hear how it was sounding like as it was. So I resynthesized those new chords using additive synthesis. So I would send these pitches and amplitudes that were kept with all the notes to a set of sine wave oscillators, so that I could create now sounds from this stage of the writing process. You see, you have heard different variations on one chord, and then it changed chord. It goes from C major to A minor for those who. So, so you see with that this how it sounded, but still it's really rough. It's really raw material, but at least I was getting to somewhere. And I processed a little bit further this new texture. To make it smoother and like more fluid-like or fluent somehow. And I used it as a background to the tape part. So here is an example of how it sounded, the final result. So what you hear now is what I call the quiet version of the tape part. And it was used in the venue while people were arriving. It was not the actual beginning of the show, it was just there as an ambience. But it was just a filtered version of the actual tape part. It was using exactly this. So you can imagine, you have to know it for sure. If you hear that, you don't think, oh, it's icicle, it's an icicle growing. But once you know it, you can imagine that what you hear it's the sounding version of this, the data of the rotating icicle that is gradually growing through the filter of the harmonic progression that I've created. Now, a next step in the composition, as I quickly mentioned at the beginning, was to think of how we would move from one texture to the other over the composition. And this was a graph that I've kind of devised. We've worked on that with Fareena. It was just to have some sort of common ground to work on the music and the visual at the same time, so that there's some sort of connection, because we didn't want to necessarily work with the music that would be really highly synchronized with the visuals. It was just like, what was the connection between our two media? And the textural type of our material was one of these elements. And so what is an underlying basic plot is what I explained at the beginning. We would move from watery motion to more what I call massive ice. I had this image of getting gradually like trapped under ice. To not quote Metallica for those who know. Anyway. So, and then the texture type is maybe what in the table followed us until the end of the process. The rest was interesting to beginning with, but we've not necessarily worked strongly with it, at least for me in the music side. So we would move from more convolution-like motion, streaming motion, flocking motion, towards freezing motion. And it will just create different moments in time in the evolution of the piece. So from those criteria, I would work I would process and transform the tape material, and it would inform the way I would write for the instrument. Now, if I give some example of what have been used to do the tape part, so as I said, it was actual recordings of snow and ice. So I had a friend who went on a frozen lake, and he recorded many situations where he was rubbing ice, throwing ice, walking on snow or whatever, many things. He had hours of such recordings, and he never used them. So I said, oh, I might need them for a project, and so we kind of found an agreement. And one example of what I've used is the following. There's many details into that maybe in another listening situation we would hear more, but this was an excerpt I took out from much more recordings that was lasting 3 minutes and 15 seconds. So to produce the material for the actual piece, I would use granular synthesis, for those who knows what is that process, and as a technique to do stretching. So I would stretch that original recording over 40 minutes, and then I would get that type of sound. Because it's like sounds of ice and snow that behave like water. And so depending on the settings I was using on the granular synthesis tool I was using, I could get this more what I call convoluting motion. Now for the streaming approach, I would use the same excerpts, still stretched over the same duration, but now with different settings to get sounds that would be more like streaming, or the way I interpreted the concept, so more on and off, like pieces of sound, if you want. So this is still a really raw material, but still you see the different textures. I was producing material, and then I would have much of that material that I can reorganize to compose a piece. And then another example of flocking this time. So a tighter stretch, now 6 minutes rather than 40, and different settings again, so that we get this more flocking effect. The idea was that the tape part will bring in the sonority of the instruments the sensation of ice and snow, so that we could almost feel that we're touching it. And so this was the idea of the immersive experience that the event should create. And here is an example of how the drone I showed you earlier was mixed with that type of material here. say too much of it because I have other excerpts where we will hear the same type of material. Now I will show more examples. So it's mostly excerpt from the actual piece that I will now present. So that we can hear the instrument combined to the drone and the tape, the sounds of ice and snow. And I will show 4 examples, one for each of the categories that I've just talked about. And what you will see on the screen is a montage that I did. Maybe Fareena will work it again in a better fashion, but still it will give an idea of the 3 screens that you were seeing in the actual installation, combined with the music. So here is an example of the beginning of the piece. It's about 2 minutes. And so I draw your attention to the properties that were used to organize this evolution over time. So at the beginning, we have more consonant sonorities and more convoluting motions. Now, an example of a situation where sound is more strict. So you will notice a different texture and also that the harmonies are more dissonant. And now more flocking. now, if we play from there, so this one is a different video. It's the video of Continuum Ensemble that they did for the actual show. So you will see the musicians now, but with the same music. So for the freezing section of the piece, I will play at the very ending of the piece. So it's a couple of minutes as well. So that we get that sense that now the harmony is really like all situated in a higher register, is still at the maximum like dissonance it can have, and the tape part is now almost static or really like hardly moving. So to suggest this idea of frozenness. That's it. Thank you.
How many people were at the design I say something. Yeah. It was a completely different experience at the end.
Yeah.
Okay. Do you make some sound? Or just
Do you need some sound?
I think at the end there's
Yeah. Were there any questions at the moment? Yeah. Yep.
The distance between the bridges was 1 centimeter.
Space.
Right. Was that set like a frequency?
Like a base frequency of the whole thing, or?
Because you were using that shape.
The shape, yeah. So the shape was determining the timbre of the raw material, and then the raw material determined the harmonies, the harmonic qualities. So the shape of the curve was really affecting the timbre because the frequency was determined by the speed at which I would repeat the cycle. Okay, so 55 hertz to get all the chords if you want, and then filtering out the chords with the chord progression I've created. So the centimeter didn't have any specific effect for the frequency. Yeah.
So it's determined.
In the sense of the spectrum.
Yeah.
Not the
time. Yeah.
Basic harmonic or something.
It's what?
basic harmonic.
Yeah, because the shape of the cycle will determine the harmonic content of the sound. And they would be tuned to the frequency to which you play them, basically. You could do this experiment using whatever sound. Once you repeat it more starting at 20 hertz by second up to 20,000 hertz by second, you will hear the pitch with the same timbre all over. So I use sound produced from those waves, but it would work with any sound. The timbre would just be different. What?
You got your display reversed, so.
It's what to see that
You're supposed to see it.
No, I think it's just when you will start it, it will just be fine. Yeah. No, it's not. But it was the same background there. That's why I thought. Yeah.
Sure, I don't mind. It's too dark. It's okay, we can keep the lights on, no problem. Oh yeah, that's good. That's nice. Start. Oh, okay. Well, hi everybody. Thank you for being here today. My name is Fareena Chanda, and I'm an interdisciplinary artist, designer, and maker. Today, I will talk a little bit about my collaboration with Jimmie LeBlanc and Stephen Morris on this project. I will begin with a little bit about my work and then go on to talk about the sort of the research process of the project and talk a little bit also about the conceptual idea of why we did what we did and how it came about. And finally, I will show you a few images and a video of the final installation that happened at Subtle Technologies Festival in May, a few months ago. So my work is interdisciplinary. I combine photography, video, installation, art practices, and sculpture in my work. Often it's heavily process-based and research-based. Everything always begins with a question which I explore through small, short, iterative experiments. Every experiment leads to sort of a new question, and eventually they amalgamate to become a concept. The work is very intuitive, and it's also very reflexive. I kind of work a lot with my gut, and that's just how it is. I use materials, three-dimensional space, and sensory perception as tools in my work. And the final work is often interactive. There's a large collective component to it where there's audience engagement and interaction in some kind of way. And it sometimes is site-specific. So for this particular project, it was site-specific to the theater center where the project was held. So when we started, Jimmie and I working on this project about almost 3 years ago now, it started with a conference in Montreal between media artists, music composers, and scientists. We were kind of paired together to make something. It was as open as that. And there was a lot of sort of random questions, common interests that led to pairing up of each person. So I was looking back at some of my old notes, and I came across this question. Can you manipulate the world to reveal something you cannot see? This is something we were talking about. We were talking about the imperceptible, making that into something that you can perceive through our senses in some way. So as we started talking with Stephen, and he was so generous to share his Icicle Atlas with us, that question became very relevant. icicles are beautiful. And what's fascinating to me about them is that they encapsulate the passage of time. In the sense of the way they grow, they make something that's imperceptible perceptible in a physical form. And that's kind of where I started my conceptual narrative of this project at that point. As I moved forward with thinking about ice, Jimmie and I both became very interested in sort of the larger poetic field of what ice is, how we interact with it, what are its characteristics. I had actually never been to a frozen lake before until last January. And that experience for me was fascinating. I come from a place where it's either very, very hot and extreme tropical temperatures or arid desert-like temperatures. So feeling the coldness of minus 40 degrees and your hands becoming numb, and it was a very visceral experience. And I was interested in translating that visceral experience in some kind of way through my work and in this project. So I explored the concept of ice and the environment of being very, very cold. I was thinking about, well, what does ice mean? What are its characteristics? Things like it's very hard, it's very sticky, it's dangerous but yet fragile, also beautiful and reflective. And so these characteristics became kind of the stepping stone to explore and start photographing ice, but also snow. I did all these nature walks when I was, this was in Lake Simcoe and then in and around Ontario. And I realized that during the winter, when the ground is covered with snow, it becomes like a blank canvas. So on days when it's really bright and the sun is shining, the shadows that are created because of the sun, they're beautiful, and they create this like ongoing painting on snow. And as the day progresses, the shadows deepen and they become longer, just in the way that the icicles grow and become longer. So those sort of natural paintings became my material to make the visuals for the project. And it kind of was natural to use time-based media to do this project, just because there's just time everywhere. So anyway, I started recording a variety of patterns on snow and collected them to make the visuals, and I'll talk about that. But a note before I continue about the haptic threshold. So the word haptic is related to the sense of touch. And it refers to the idea of perceiving something sensorially. And the haptic threshold was a concept that Jimmie and I spoke about a lot before the project really even synthesized. And we were really interested in this idea where an aesthetic experience moved from a sensory realm to an intellectual realm and vice versa. And this kind of an idea was really the backbone of how we progressed through our explorations and our process. So Jimmie spoke a lot about this chart, and while he was exploring sort of this movement from the sort of a water phase to a massive ice phase sonically, I started exploring the same patterns visually. And so as I was saying, I filmed different times, different places, these paintings that were being sort of naturally drawn on snow, and then not necessarily match them exactly to Jimmie's compositions, but really try to get at the emotions of the composition and harmonize the visuals with the sound. Once that was kind of well underway, it was time to sort of think about the installation itself. And one of the key questions at that point was how to create an environment where we could sort of touch on this embodied knowledge that exists of how we think about ice, feel sort of a cold environment, and bring that out through the installation itself. We were constrained by obviously the space itself, so the project had to be site specific to the theater space. So the way we designed the installation was 3 large projection screens made in a cube-like room. It was about 12 feet by 12 feet wide. It was a square. And the videos were back projected. And the floor, we installed the metal flooring to create a lake effect, but also to sort of show the installations on the floor, and so it could also reflect back into the environment, and it created this sort of very immersive, overwhelming kind of feeling. And then what's interesting about installations is you think of something and then something happens. That's just the nature of how people come together in a space. You don't control things after a certain point, but that's also the beauty of this kind of work. Whereas I had originally imagined people to move in and out of this space during the performance, because it was a lot like a concert. People naturally ended up sitting in that space. So the experience itself ended up being a very cozy, collective experience. So I have just a short video here of... composition was about 20 minutes long. So this is just a small and it really moved very slowly through the environment that's constantly changing. That's it.
Thank you. Yeah, we all go to this age and we see some
Questions
for the 3 of them.
It was 12 feet by 12 feet. Mm-hmm.
Some questions.
They were different. They were each slightly different from each other.
And so, but they were synced so that they all started at the same
Yes.
time and the same thing happened.
Yes.
And
yes.
was there manipulation in terms of the footage?
There was a lot of layering of many different videos, a lot of layering, a lot of editing the video to match the mood, the textures of the sounds, and sort of the density of the sounds as well. So I manipulated them in that way. Mm-hmm.
Yeah, I don't know. That's comfortable. I don't know where you talk. I think you got to that one. Yeah.
Yeah.
Stephen, on naturally growing icicles, are the ridges the same dimension?
Yes, as far as we know. It's remarkably difficult to gather a significant sample of natural icicles. We've measured a few of them, but not anything like as many as we have in the atlas. And the other thing about natural icicles is you don't know what their water source is, you don't know what their growing conditions are. So we don't really know very much about natural icicles, except I have a few hundred pictures of them, but we don't know the history. I did collect a bunch of icicles off of my neighbor's garages. I was all set to explain myself if anyone stopped me, but I did never get stopped. And we sent them to the chemistry lab to have their water composition analyzed. And it is true that the icicles that have ripples on them are a little tiny bit dirty, their water. But it doesn't take very much, So the rainwater, if the rainwater didn't run over the roof or anything, it would probably be so clean that it never produced ripples. But because it runs over the roof and picks up air pollution and stuff like that, it's probably dirty enough to produce ripples.
I thought raindrops form dust particles.
Yeah, so it does have a little bit of acidity, which comes from air pollution and soot and things like that. So I can tell you the composition of a whole bunch of random icicles, and they're all over the place. They have all kinds of stuff in them. We also analyzed Toronto tap water, and we have some measurements of tap water icicles. There's all kinds of interesting metals and things in Toronto tap water. But for the experiment, we used pure sodium chloride and pure water. So there's, if one were to make music of all the icicles in the atlas, it would take an awfully long time. Because all of what you heard was made from one icicle, even one side of one icicle. Other questions?
Okay, I'll let people think about questions, but I have a question which has been kind of making its way while I was preparing for this event. And I think that Stephen kind of figured it. Well, you said, and the question is for the three of you. You said that all that music, all that was only for one icicle. And this gives me this idea of the huge complexity that is in these ideas. And Fareena is describing all the shadows and like all the different patterns that you can get when you are in the field trying to record things. And also like I was struck by the minutiae that characterize the recreation once only one item is recorded. So I'm wondering, in front of all this complexity, I'm wondering this project in particular that you made, might actually cast some light, bring some light to, or make things more human for public that is not like is used to see these things on a daily basis and don't necessarily understand that there's like a whole complexity behind it. So I'm wondering if this is creating new ways for us to understand and to view natural phenomena.
Well, that's the famous quote of Blake, who said that he could see the world in a grain of sand.
But you cannot really see it.
It's there, though. The whole history of the Earth, and the formation of the solar system, is implied by every grain of sand. And so I think the rather obsessive attention that we pay to icicles is part of the message. Really, it's not entirely about icicles. It's about looking. Right? And the more you look and the harder you look, the more phenomena you see and the more mysteries, come to your mind. People have been seeing icicles but not seeing them for a long time. If you really think about them deeply, it sounds nuts, but the reward is not just that you learn about icicles, it's you learn about the depth of phenomena and what's there and the intensity of your experience looking closely is part of the message of the project. In my mind, that's part of what it is.
I think so. As an artist, I think spending that time in the field is in itself a way of looking very closely. And through the work, the goal or the intention was also to create that moment where you could kind of spend that time to really let the sound and the visuals kind of wash over you, and you slow down to take it all in. So I think there is an element of looking closely.
Yeah, and I think what was interesting also is to think in terms of what is the sensation of eyes if it's not, well, even when it is like touching it actually, in terms of on the music side of the collaboration, I was not really interested in reproducing a general soundscape that would be more like looking at eyes from, I don't know, a farther point, or like how we could have maybe more imagined, because we imagine eyes like landscape as something almost desert, really wide, so we would imagine things from a distance. Which maybe would be the more natural way of thinking of it and listening to it. If I can think of different recordings of pieces, I know that maybe that work with this imagery. I wanted rather to explore the violent nature of eyes. It's not violent by itself, but imagine there's a big difference between walking on ice, like properly dressed, and properly dressed, so you're not too cold, but you're just walking on ice and it's sunny and you are there and you admire the landscape, and being into ice. Imagine that. It's not like being into water. Water is sweet, if it's not too cold. But ice, if you are in ice, it's quite violent if you freeze yourself into ice. So I had kind of these ideas of what it would be like to be in the middle of an icicle for me.
Poking you with icicles.
So it's like Han Solo Carbonite's frozenness in Star Wars. It's not funny. At least you preserve for a longer time, but but it's not like. So I was trying to imagine, and it came out as a word when we were talking about eyes, like that. It has something violent, even if it's like.
This is a very Canadian topic.
What it is, maybe.
Yes, and in this moment, one wonders where eyes is, because we haven't seen any.
Well, kiss your icicles
No,
goodbye.
well, not in the north, believe me, I'm working on it. So, but there hasn't been any eyes. So one of the things that came to our mind when we organized this event was, it's going to be in December, it's going to be all about eyes, it's going to be like an outside, and people are going to be able to experience what it feels like walking on ice and feel the ice, because outside is going to be
inadvertently we have a climate change theme here.
But it is not. Yes.
Yeah.
Well, we're all glad we're not long now. But a couple of things. One was that, sorry, I'm obsessed by this 1 centimeter thing.
You should be.
No, just because if you said there's only one icicle, but if they all have this thing, then actually there is a unifying thing.
Yes. We believe it's a universe. I should also mention that stalactites have 1 centimeter ripples as well. And stalactites aren't ice at all. They are fluid mechanically similar, but otherwise quite different. And there's some connection between the two.
The other thing, sorry, being so scientific, I can't help myself, but
Let it all out.
Is there any reason to believe that icicles will form on a rotating basis or the same icicles formed on the side?
Well, we rotate really slowly.
But I mean, you can still see the film. You see the angular.
Oh, but that's not nothing to do with the angular momentum. If you watched it in real time, you wouldn't think that. I mean, the stresses on the surface due to the airflow are huge compared to the stresses due to the acidity. The thing's in a turbulent box, right? So everybody says that. They think it's going really fast. But if I showed you the movie of this icicle growing, we would have had to start this morning at about 9:30 or 10 o'clock, and maybe 2, 3, or 4 o'clock in the afternoon, we could watch it reach the maximum length. And it moves. The rotation is rotation every 4 minutes, so it takes. You can see it rotate if you look closely, but
even still, that's not the way it's performed.
no. But we also grew some without rotating them, so I'm not worried about it. I'm not worried about the rotation.
So I'm interested in the collaborative model that we're looking at here, and what the collaboration means, because it seems to have gone from one to the next, and there might have been a little bit of overlap between number 2 and number 3, but did anything go in the other direction? Because I guess I have an assumption that collaboration is interaction, when in fact it seems to be almost linear.
Well, Jimmie and I worked quite a bit. I mean,
I guess I was the middle connection.
Yeah, kind of the middle guy. So it's not that I just handed them the data and we all went home. It's we had to work back and forth quite a bit on making the thing work. But I have to admit that the physics experiment has not been influenced directly by the music.
No. So you haven't changed your working methods or understanding. In fact, you've got a really interesting model of because probably more intuitive approach. Whether, like hopefully you all benefit?
Well, sort of. I've certainly played with the data in an artistic sense much more than I would have otherwise.
Because I was asking him, for instance, to format those curves following certain criteria for me to be able to use them in my own software and then to process them into something. So so for me it was informing the way I would compose the harmonies of the piece. But then the general poetics of the project was to go into the larger realm of sensations associated with ice in general, and not necessarily icicle. And that's where then we were connecting with Fareena, so that the visual was larger than icicle, but still, of course, the connection is obvious. And in the music was somehow working with the more general sensations on the macro level, but with the scientific data on the micro level. Maybe we could see it this way. And also we have, maybe it could also answer your question in another way, is that when we first met in 2013 in Montreal for this pairing conference, Steven was not yet in the team. So he came a little bit later in the project. So we had already started to, and we were not necessarily talking about ice at the beginning. In fact, ice came with you.
Yeah.
Because the scientist with whom we were associated at the beginning, we were paired at the beginning, was working on ultra cold atoms. So there's a connection.
Boy, they're cold.
There's a certain connection, but the general topic that we were working on at the beginning, it was even not necessarily atoms, but it was this idea of the haptic threshold. So it was really like beginning stages. We didn't know what we were to do, but we knew that we were interested in working in those sensational phenomena that would bring together music and visuals. So then it built differently, but. Yes, I kind of been the synthesizer of two sides. Yeah.
So the Icicle project, its purpose has enlarged. It's about more than just the basic scientific publications and so on. I mean, I now think of it as a kind of broad program of things. And I'm interested in making images. I was thinking we could use some of the music to accompany the icicle growing images that I put on the web and things like that. And I use it a lot for outreach purposes. So what you call an art event is for us inside scientists an outreach occasion. But in fact, they're exactly the same thing. We don't do anything different. So I've done a lot of presenting of this kind of work to audiences who aren't interested in science as such. So it becomes quite mushy as to whether it's an art project or a science project.
But it's not just for outreach. I mean, I can see that, like, if you take the icicle and the formation of the icicle, and you have either graphics or music accompanying it, like, I think it enriches it gives you a better idea of the data that are being communicated. And, like, maybe correct me if I'm wrong, but I think that in terms of, like, scientifically speaking, it augments the type of knowledge that.
Yeah. Well, I'm interested in
spreading this stuff
quite broadly, right? So it's not just about
squeezing scientific results out of it.
Yeah.
I wonder if music, from your point of view, the fact that we as humans, we are sensing only certain notes sounding good, could this be a kind of effect? Only humans are effective and they see only together sounding good, C major or C minor. Basically, the question, would other species consider music all sorts of frequencies together, and they might sound...
Dogs would have a wider range of...
Yeah.
Yeah, well, there's maybe, I don't know if I understood correctly, but there's maybe two things in your two elements in the questions you asked. First, there's the audible range of what we actually hear, and of course, we could generate data, sound like sonic data that we would not hear as human, but still that could be heard by a dog or by other. So I didn't work really with that. Otherwise, then I really needed to use frequencies that were in our audible range to be able to hear something myself while I was working. And
the other aspect of your question
regarding the chords, the harmonies that I've chosen, I could have decided not at all to work with that. It's really like this is a musical, editorial, aesthetic choice to decide, okay, we'll use major triads and minor triads to kind of harness this really rich and proliferating material, just to avoid maybe chaos. But because even in the triads that I've used to filter out the really rich harmonies, there's still complexity, a really high level of complexity. So it was really a way to bring things up, to find some sort of an anchor, to bring things down to a certain level of control, and to let the complexity express itself in that frame. But I could have decided to work with a non-harmonic aggregation of pitches, and it would have been a different music, a different result. The tape part was bringing this sonic complexity because it was actual noise. So this has the kind of white noise and filtered quality you can add to it to manipulate it, but it adds this really complex sounding quality. So the instrument part was bringing, and the drone was bringing a little ground to it, and was a good way for me also to create some landmark in the evolution of the piece, because we could hear when we were moving from one triad to the other, and in between, all the kind of the oscillations of the same triad with all the micro variation into it. So it was a way to build the harmonic structure. But this is how I did, and what I was thinking in an earlier question is that a different composer would do something completely different. And you said that I extracted complex data from, because the way I did it but I could have done completely differently using 50 icicles, but using more simple element of them, and I could really, and someone else would have a different idea. It's not the music of Icicle, it's one music from a certain approach to the data of this exploration, and it's infinite what you can do with
the path from the Icicle to the music.
Exactly.
Straight.
And I wanted to, when I saw the waves, I thought sound waves, and I was teaching an electronic music composition course at that moment, so I was really into electronic things. So I really thought, okay, sound waves, let's try that. I never did wave shaping, so I wanted to try, and discovered some new tools for my personal use as well. It was really an experiment. I really took it as an experiment. It's quite different from what I'm doing usually, actually, the final result. I really kind of took the occasion to explore a way to do that I never did before, actually. Yeah.
I mean, there's another way to look at it. You may ask, why do people care about why do we find the ripples interesting in the first place? The answer is that they're regular. They have some kind of your eye is drawn to say, wow, something needs an explanation there, or something is happening here that's not just random. They're all 1 centimeter, so clearly there's some process that we don't understand there. But that's just your evolution picking structure out of the randomness of the world, right? And I think there's a sort of musical component to that. You listen to things, and you find sounds interesting, which are not random. They have some kind of structure to them. And so while we look at the icicles, we find scientific questions in exactly the thing that our senses are evolutionarily designed to pick out of the noise, basically. So the ripples are a striking thing because they seem to be regular in a place where you might expect, nothing interesting to happen. But here, this sort of chord-like, if you think of them as a sound, they make a nice pure sound because they're such a nice pure-looking ripple pattern. And I confess to have thought of them as sounds before meeting Jimmie. I thought maybe it would make a kind of ping noise if I could play this sound, right? So I envision an experiment where the icicle rotates and a bunch of metal fingers go up against the side of it and play it like a player piano or something, a mechanical gadget. Or maybe a whole bunch of icicles that you could play like a xylophone, driven by...
An icicle-ophone.
An icicle-ophone.
Exactly, if you could move them like in a resonant material with different length. When Christmas is coming, you could sell instruments. I'm sure it would work.
But all these things come from the same source, which is that you look at the structure in the world and not just random complicated things, but things that have seem to demand some attention from the art. And ripples just, to my physicist's eye, ripples are just, they demand my attention, and that's like a purely, it's the same way as a melody demands your attention as a
there's a research question which seems to have influenced all of your work, but there's also something that Fareena was describing, and that's something that was coming from the gut, so something that is very, you're not scientists, you're not
No, I agree with that.
But there's like intuition involved.
That's right. I looked at the icicle and my gut told me I had to explain it. Right? Yeah, no, the gut's just as important as science. I think, I meet lots of scientists who are studying things that I don't find interesting because they don't appeal to my gut. It has nothing to do with any kind of analytic rules or anything. It's all about, I know what it's interesting when I see it. Yeah.
Could there be some kind of feedback loop, so maybe the music could affect subsequent icicle experiments somehow?
Well, I think it has, in the sense that I just think more broadly about the...
Maybe do something more specific in terms of maybe some of the theories be driven by some of the musical constructs.
Can I start playing music to the icicle?
That's fine.
It's tempting.
So good.
I've got tenure, so I can do whatever I want. The distance is bigger than that, I think. Our picture that we were talking about before with all the boundary conditions and equations, that's a whole core dump of junk that I didn't explain. But in the back of this, there's a truckload of mathematics and a truckload of computation. And I haven't, like a good dentist, I have not revealed my tools to you. But in fact, that's where the sort of, the aesthetic backstory of the physics is mostly. It's not just in the visual, but also in, again, some of the equations, which is hard to explain to someone who doesn't know a lot about math. Maybe you do, but yeah. So the project had another whole dimension to it, which I haven't discussed.
But sometimes it could happen, because what is interesting, I find, in arts and science collaborations is that we can use any data and try anything as artists, and it doesn't matter if we do a mistake or if we fail. But if in science you do a mistake, it can have much more.
People make mistakes all the time.
No, Matt, it depends on what you work as, on what you're working on as well. But what is interesting is that because we can try things without knowing exactly everything of those truckloads of mathematics and all that, sometimes by accident we can just arrive with something, hey, look at that, and then the scientist would say, oh, maybe it can inform what I'm doing in some ways. So I don't know if maybe on that particular case it didn't happen this way, but these are things that can happen when we collaborate together, because we would do things that a scientist would not necessarily think of, and conversely, things with the data I would do and suggest me that I would not think of doing with it. And so we have a different view of the same object.
Well, I'm just going to say that as a scientist, we also don't publish our failures, right? You probably don't have an art show of stuff that didn't work, or you even present a symphony that didn't work, right? And so there's lots of failures.
Well, we don't publish
very much. It doesn't work at all.
We don't publish very much of the whole process, really. The output of the sciences is just incredibly dry and boring stuff, typically. And when you give a talk about it, you get to show more of the backstory. But even that doesn't really explain it very much. So one of the things I like about all these kind of things is it allows you to kind of get out of the box a bit. It's a very unsatisfying project if all that came out of it was the scientific publications.
Just maybe some of the Python code could be dictated by some of these goals.
Oh, it was, yeah. I mean, I wrote code to make the waveforms for him. So.
I mean, you can just
The other way around.
Yeah. So I guess I envision a kind of a code that would give you a musical piece and some icicles to look at, all based on mining the data. And, yeah.
What could be interesting is if working on a wave, for instance, and manipulating it and creating a sound object, and then reconverting it into a wave that it could use to direct the formation of an icicle following that way, but it's impossible, I guess. But this would have been some sort of
it's quite possible.
Yeah?
Well, you can modulate.
You should work on it.
You can modulate the water flow or the temperature. So,
who knows?
yeah. I mean, we built this device partly for our own obsessive amusement. So the device isn't, we call it the Icicle machine because it's not just an apparatus for making data. It's a machine for making icicles. And our purpose there is more broad than just acquiring the data. You see what I mean? I've thought about, I tried to sell the Exploratorium in San Francisco, an icicle machine to sit on the floor of the Exploratorium as a science center demonstration. And I've thought of it as a potential, gallery installation of the machine, And, well, it's a bit complex, so it hasn't happened yet. But maybe when the icicle machine may yet retire to some art purpose. Yeah, there was a question over here somewhere. Yeah.
Was the choice of making music that acts here as an expected role caused like the constraints that it would be in the first installation? And if it was, didn't have those constraints, discerning the patterns from the data, producing differently, perhaps a bit more melodic or harmonic, or perhaps instrumentation.
No. Well, yes, they were constrained, but we decided on the constraint. So it was to, I think I was really interested in the textural element of it, and I'm not really working myself melodically, generally speaking, or so I don't know. I thought that I knew we wanted the music to be immersive, so I knew I would work in a textural way. I knew that, but I didn't knew what I would do with the data. It's by looking at the data and suddenly saying, oh, I could try to make them sounding waves, and then it was interesting. So, I could analyze them and see what is the actual content, and then so it's really like step by step without knowing exactly. I knew the general principles, but the detail of the realization, I really didn't know. It was just building along the way. Now, if I would rephrase your question, would I do another piece from the same set of information in completely different context, like a concert piece, or I don't know? I don't know. And depending on, because the general poetics of the whole thing was not related to the research at all. We wanted to do something immersive, something more sensorial. Just because that been done without using Icicle data somehow. It could have been done using whatever. This was just a kind of information that we would use to make the music in that overall context we have thought of. But I don't know if I would, but I could, of course, do something completely different from the same data. Yeah, and someone could have used the same waves to do a melody, actually. We could have used that in some ways to create melodies like this. This is not at all what I did, but it could have been a way to use the same data in a completely different fashion. Does it answer? Have I understood? Yeah.
The data, by the way, is open source, open. So feel free to use it for whatever purpose you want. Thank you.
Thank you.
Tune in next in January.